All right. Well, good morning, everybody. Can I get a good morning? Everyone seems a little dreary. So what I wanted to cover here today are a few things that we've been doing, investments that we've been making across the stack, places that we've been pushing forward on the technology and on the underlying infrastructure of this whole thing. So through the entire stack here of Kubernetes and this whole container ecosystem, CoreOS has expertise across the whole thing. So we've been investing from anywhere from in the operating system with container Linux all the way through to Kubernetes and what we've been doing with Tectonic. So I really wanted to go through and cover some of the things that Alex didn't have the opportunity to cover yesterday during his keynote. These are things around the container engine and container specifications, around identity and management, the primary data store of Kubernetes etcd. And then we'll be talking about some of the architecture that actually enables self-driving Kubernetes that we talked about yesterday. So the first thing I wanted to talk about here was around the container. The container is really the shared infrastructure of this whole ecosystem. It's the thing that allows for mobility of the applications. It's the thing that allows us to move things around and manage the workloads. And so we think it's really important that this shared foundation be built on top of standards. And for the last couple of years, this has been something that we've been working really, really hard with the rest of the industry on. So in June of 2015, us, Docker, Microsoft, Google, a bunch of people got together in the Open Container Initiative. And the idea here is that we're trying to create good, solid specifications. And we're doing it in a different way than specifications have been built in the past. We're doing specifications more like open source projects, doing more rapid iteration. And our hope here is that we're able to create for both the runtime and for the image specification solid things that people can rely on for years to come. So over the last 18 months, we've been making good progress. We've been making RC releases of this specification. And then going into early 2017, around the 20-month mark of the project, we should be hitting OCI 1.0. And so I just wanted to reflect on why standards are so important. The main thing is that initially that it creates a lot of communication between engineers working on different projects. It's really easy for things to look like they work trivially, but then when you dig into the details, for them to not to work. So having standards is important there. The next bit is that it allows for interoperating products. I think the big power of containers that has been enabled over the last couple of years is it delivered on the promise of cloud mobility in a way that we really never got with VMs. The standardized ways of shipping around VM container images or VM images around between different clouds never really emerged. But with the container, you can actually reliably run the same piece of software on various Linux systems in any environment. And then the last bit is around building stability. So people are going to be packaging up applications today that they want to run on infrastructure 5, 10, 15 years from now. We see this with a lot of our customers. We talked about this with Ticketmaster yesterday. These are long-term investments in infrastructure, and we want to ensure that the things that people are building are the right things for a long period of time. All right, so the next thing I wanted to cover was about Rocket, which is our pod native container engine, a project that we started around 2 years ago. With Rocket, we've been pushing along on getting a bunch of different community users. Rocket has found a really strong niche in various places across the container ecosystem. The first is that we've started to work with integrating Rocket into Kubernetes. You can enable Rocket support inside of Kubernetes with a single flag. Minikube is this tool to run run Kubernetes on your laptop, and you can enable a Rocket with a single flag. We have public users that talk about Rocket quite a bit. This car sharing application that you may not have heard of because it's European and it's difficult to pronounce, called BlaBlaCar, has used Rocket in all of their production systems and is moving to Rocket with Kubernetes in the coming year as that support matures. Container Linux uses Rocket internally for a ton of different services. If you use Kubernetes at all, the kubelet is being executed under Rocket these days. etcd is being executed under Rocket, et cetera. And then Google's GK Container VM is looking at using Rocket as the way of managing mounts. So Rocket has found its way as this kind of system-level containerizer. And then we've been working on a ton of different things on the Rocket roadmap. Most importantly is that we're integrating Kubernetes and Rocket together. Alex touched on, and we talked about it in the video, Kubernetes has a very strong engineering culture to the point that it can be frustrating to get the features that you want into Kubernetes, but we always end up on the right solution. And so we've been working and helping to refactor some internal systems in Kubernetes, which I'll cover in a second, around CRI. We'll be supporting all the OCI standards as they go into 1.0. Currently, we support release candidate versions of the image spec, and we'll be pushing that forward going to 2017. And then the last bit is that we continue to innovate and investigate new ways of doing security and design of these systems, and I'll touch on that in just a moment. So let's focus on CRI and Kubernetes. So a quick reminder on pod basics. So pod glues together a bunch of different containers. And then the pod is the primary unit of scheduling inside of Kubernetes. So a pod, you can think of Kubernetes as having these strong hierarchies. So a cluster schedules a pod to an individual machine, and then the pod has its own lifecycle on that individual machine. So we have a Kubernetes cluster that looks like this. You have an application that you describe as a pod, A1. You put it into kubectl. It ends up on a host, or maybe you have some long-running job, and then that ends up on a host. But if you zoom in on what's actually happening there, it's just a bunch of container images executing as processes. And what we're doing with Rocket is we're making these processes execute and be dynamic underneath the Rocket engine. And CRI, the way that Kubernetes manages these processes, can get pretty dynamic. So as an example, we have Kubernetes health checks. And so Kubernetes will say, this process's health check has failed. Can you go ahead and just restart this one process inside of the pod? And this is all kind of new APIs and abstractions that we're integrating into Kubernetes through this concept called the Container Runtime Interface, and that we're implementing directly inside of Rocket, things that Rocket understands natively. And we think that having a container engine that really natively understands Kubernetes abstractions will lead to a bunch of rapid innovation inside of Kubernetes once we get to full integration. Right now, we're at about 90% integration. Hope to get 100% over the next couple of releases of Kubernetes. And then we can start to play around with this concept of pods even further in the ecosystem. The next thing is just support for all the OCI standards. So today, we can download and execute OCI images, just like we can download and execute Docker images underneath Rocket. We'll also be, and we've started to integrate the runc, which is the container runner from OCI, to actually just execute each individual process. So Rocket will set up the pod sandbox, and then runc will actually execute the individual processes and manage those life cycles. This is work that's ongoing and that we'll be completing early next year. And then the last bit is design for security. So Rocket is the only container engine that allows for both Linux native isolation and VM isolation. If you haven't seen this before, the big idea is that generally a container executes on a shared kernel, and that shared kernel, so each process essentially interacts with that shared kernel. With container VM isolation, we actually wrap each pod in its own kernel, which means that if there's a privilege escalation inside of the individual process, it doesn't necessarily able to get out into the shared kernel. And so what we've started to explore are what are ways of actually detecting this privilege escalation using these virtual machines and using Rocket. So a normal process lifecycle looks something like this. You have your process, maybe it's a bash prompt. You want to create another process, and what you're trying to do is actually execute a process as an elevated user under root. And so you fork the new process, you exec to su, you get elevated permissions, and then you can execute bash as like a elevated user. This is a normal, healthy execution elevation, or privilege elevation inside of Linux. Now, something that we want to protect against is somebody exploiting maybe an issue inside of the Linux kernel, and we want to be able to shut the container down. And so you have bash, bash forks off another process, and then maybe you're able to read a certain file under the Linux kernel, which causes the process to have escalated privileges. At this point, we want to be able to shut down the container or maybe pause it so that you can do post-mortem analysis. And so what we've done is we've built a prototype that's up as a pull request today on Rocket, where we actually create this external state machine from the Linux kernel, and we watch all the processes and their states and see if any of them make invalid transitions. And so what this enables is we can say, maybe you have this debug agent, it's allowed to do things as root, and that's totally fine. But maybe your web server, somebody uploads a rootkit payload or something, which knows how to take advantage of some issue. It asks this external monitoring agent, well, is it OK for this process to make this transition? And the validator says that's not a valid transition and actually just stops the container VM altogether. And so this is an example of this whole process working. So we create a process as we create an interactive terminal prompt with Rocket. We try to run a process as a non-privileged user. We have an exploit in this kernel that we introduced for demo purposes, that when you open proc interrupts, it actually gets elevated permissions all of a sudden, kind of a trivial privilege escalation. And the container VM just shuts off because we're validating all these process states. So it's a pretty cool piece of technology, something that's kind of unique to the capabilities of Rocket, and areas where we're starting to investigate and look at new ideas in security. All right, and with all that Rocket work and news, I want to just reiterate that CoreOS inside of Tectonic will continue to support users no matter whether they choose the Docker engine or the Rocket engine. This is important. We support users if they want to change out storage or networking or identity inside of Tectonic, and we see the execution engine in the same way. So another thing is about Kubernetes scale. I talked about this a little bit last year at Tectonic Summit. And really, this is important to a lot of users because they want to know that when they choose this platform, it will continue to scale as their business scales over the coming years and 5, 10 years out. And so we've been doing a lot of work at CoreOS to ensure this is true, working end-to-end to ensure that Kubernetes can scale. A quick reminder of the architecture of Kubernetes. It's really, if you think about Kubernetes as just a generic web app, let's think of WordPress, for example. So you have WordPress and MySQL. In the world of Kubernetes, it's the Kubernetes API server and etcd. And so you have this horizontally scalable API server, and then everything is persisted into the etcd database. And so etcd is this database introduced in 2013, primary persistent store of Kubernetes. And it has all these special properties around auto leader election and that sort of thing, so you don't get paged in the middle of the night if an individual instance of the database fails. So etcd is this foundation of Kubernetes, and CoreOS has been working to ensure that it's scalable, simple, and solid for all these different environments. So when Kubernetes hit 1.0, the first scaling goal was 100 nodes. And then a few months later, we hit 1,000 nodes. And then earlier this year, we hit 2,000 nodes. And then with the latest release in 1.5, it's possible to scale Kubernetes pretty reliably up to about 5,000 nodes. And a lot of this has been done with some of the work that we've been putting into etcd to make it scale really well. And we've been doing all of this work by profiling and benchmarking and working with different upstream communities to ensure we're using best practices in how to design consistent key value databases. We have a really in-depth report on benchmarking and our findings and how to build a database that scales coming out pretty soon here. But this is kind of all the options that people have today in these consistent key value stores. And we're really happy to say that etcd is, in the last few releases, the most performant on latency and network and the ability to do write throughput. And we have to discount Google Chubby because that one's closed source, so we can't actually benchmark it. Zookeeper is a long-running one, been used in the Apache ecosystem, and I'll compare essentially etcd and Zookeeper here in just a couple of slides to give you a preview of some of the benchmarking we've been doing. So this is about storing 512 megabytes of data, which is a pretty substantial amount of data in the world of Kubernetes. This is a pretty large cluster. And so for storing 512 megabytes of data, etcd has about a 30% overhead, and Zookeeper has about a 5x overhead. So it's chewing up about 2.5 gigabytes of data resident. This is a pretty key scalability metric because people are wanting to run large clusters really efficiently and capital efficiently on these various clouds. The other really important scaling metric is latency. So nobody likes getting woken up in the middle of the night because some system is flapping. And latency is important in these systems because latency looks like failure. And so in this graph, lower is better. And I'm really happy that we have to zoom in to see etcd's latency here. So etcd is that thin blue line really close to the bottom. And Zookeeper is the spiky lines. And this is because we focus on ensuring that etcd doesn't ever hit garbage collection in really spiky ways. And so what this means is that when you're setting up your monitoring, you can say, this is the window that etcd will perform in. And you don't get woken up just because there's some transient garbage collection happening inside of etcd. So we've been doing even more and more benchmarking, simulating larger and larger Kubernetes clusters. And we're pretty confident that etcd will scale up to around 20,000 Kubernetes nodes with no issue. And so that will help move the focus to other parts of the Kubernetes scaling properties around the kubelet and the API server, et cetera, over the coming year. And etcd will be able to keep up quite handily. The next thing is about simplicity. So etcd is a distributed database, and these things are inherently hard to operate. And so we have introduced this concept called operators earlier this year, talked about it at KubeCon. The big idea here is that we help to automate some of the life cycle around these distributed systems. So it's much easier, much more Kubernetes native, where we're able to declare, I want a three-member cluster of etcd. Please, Kubernetes, can you manage this using the Kubernetes APIs? And this will become ever more important when we start to think about things like David Aronchek demoed yesterday, where we want to federate Kubernetes clusters over larger and larger different environments. You see here that, once again, etcd is pretty key to federation. That's the primary data store of the federation API. And if you zoom in on that diagram a little bit more, you need to have the federation API also replicated over multiple data centers so you don't lose your federation data. And that's where we want to start operating these etcd clusters in these globally available ways. And then the last bit is about making a system that's really solid, something that you feel confident running in production. And the team at CoreOS does a ton of work to ensure that all these various punishing tests happen against the etcd cluster. We remove disks. I'm happy to say that we found a bug in the Linux kernel's tempfs implementation earlier this year, which I feel is a certification that we might be testing pretty hard if we are fixing upstream tempfs bugs. So we're making a lot of progress to build a system that is resilient to all the really common hardware and network failures that you'll encounter in production. And I'm really happy to say that etcd isn't just used in Kubernetes. It's being trusted by hundreds of open source projects. And even better, there's been teams from Google and Amazon and Microsoft now who have open source projects that are built on etcd. Just in the last 2 weeks, Amazon and Microsoft have built things and open sourced them using the etcd database. All right. So yesterday we talked about self-driving architecture, or self-driving Kubernetes. I want to talk about the architecture that enables self-driving. What we're trying to do is simplify the operation of Kubernetes. And it's using this concept called SelfHosted. It's a little confusing. There's self-driving and there's self-hosted. They're different ideas. So I'm going to use the example of Linus Torvalds, who wrote the Linux kernel. So this is young Linus. I don't know if this is anywhere close to what he looked like when he started writing the kernel, but we'll use this picture. And so Linus, at the time when he was writing it, only had a Unix operating system available to him called Minix. But he wanted to build his own operating system. So he's writing Linux on top of his Minix workstation. And then out pops a copy of our beloved Linux. And then a few months later, for drama, I've put up a photo of Linus years later. But a few months later, Linus has Linux running. And so he's ported all of the tools required, like GCC, over to Linux. And so he's able to use Linux to build Linux and then reboot into a new copy of Linux. This is kind of the idea that we're going for with self-hosted Kubernetes. We're wanting to manage Kubernetes using Kubernetes APIs. And so the idea here is that you have your dedicated control nodes, you have your dedicated worker nodes, and you put inside of Kubernetes pods, you put all the control components of Kubernetes in pods, download them as container images, and you run them on a dedicated set of nodes. And so say we have that monitoring service, and then we want to scale up our Kubernetes scheduler. So we kind of make a little room, because fonts are hard, and you move the Kubernetes scheduler onto another machine. Now you have an HA Kubernetes scheduler. And the whole thing is done using essentially the Kubernetes API. So as a practical example, here we're looking for the Kubernetes scheduler in the Tectonic console. We say we want to move from 1 copy to 2 copies. A few seconds later, we have 2 copies running. And that's all done via the Kubernetes APIs. There's no other automation that's being used. We're using Kubernetes to manage Kubernetes. And this has been kind of a long-term goal of a lot of the original people working on Kubernetes is how do we use the Kubernetes APIs instead of inventing kind of this underlayer behind Kubernetes. So that's the architecture of self-driving, is that we've worked upstream with the wider community to figure out how to use Kubernetes to manage Kubernetes. And we think that it removes a lot of toil, a lot of hard work from these systems. If you haven't read, this is a great book, the Software Reliability Engineering book by O'Reilly. But they describe toil as essentially anything that can be automated away. And we feel like operations of Kubernetes is something that can be, to a large extent, automated so that people can focus on running their applications and getting value from Kubernetes. I don't think it's important that people understand the configuration file syntax or all the details of making a highly available Kubernetes cluster. We should allow them to use the same things that they do to make their application highly available for the Kubernetes actual infrastructure. But of course, failures happen. Like you have a self-driving car, but that doesn't mean you can ignore the check engine light, or that you don't have to plug it in, or that the gas never has to be refilled. And so the other advantage that this architecture has is that we're able to use the exact same APIs and functionality that we have to monitor our applications, to monitor Kubernetes. So here's a practical example. We use the Prometheus monitoring service to monitor all the components inside of the Kubernetes clusters that we deploy with Tectonic. If we can do a CSI style, like zoom in on that console there, what it looks like is we can go see, here's the Kubernetes scheduler, and here's the RAM, here's the CPU that process is using. We can go and introspect the logs, et cetera. Now, of course, there's all sorts of tricky situations you get yourself into, but those situations are pretty small, and we've documented a lot of where things can fail and how you recover from it. I don't think anybody will say that managing a Linux operating system is difficult just because once in a while you have to go drop down to the single user mode. All right, and I'm really happy to say that self-hosted is being pretty widely adopted by the Kubernetes community. There's a bunch of different tools that have been built to help install and manage Kubernetes, things like kubadmin. In the next release of Kubernetes, we'll be using self-hosted as well. So this isn't just something that we're doing, it's a wider set of technologies and testing and everything that's going into the idea of self-hosted. Now, the last thing I kind of wanted to touch on was about user identity. So we have this example of this Kubernetes user using kubectl on their laptop. But how do you ensure that that user is authenticated? Or more importantly, as we start to think about federation, how do you ensure that user has access to all 3 data centers that you're running? And so what we've been doing for about the last 18 months or so is building an open source project called DEX. Now, DEX is built on OIDC, known as OpenID Connect, which is one of the world's most confusing standards names, period. Who here has ever heard of OpenID? All right. Who here knows the difference between OpenID Connect and OpenID? Exactly. So OpenID Connect is essentially OAuth 2, and OpenID Connect is used by essentially every major identity provider on the internet, Google, Salesforce, et cetera. They all use OpenID Connect. And so we've built an OpenID Connect provider that people can back with LDAP and other enterprise systems. And then we've integrated that into Kubernetes upstream. So we've plumbed through OpenID Connect cryptographic tokens to the entire system. And so when you log into a Tectonic console, it's using OpenID Connect. When you use kubectl, it's using OpenID Connect. And we've also happily built DEX 2.0, which is released as a final release today. And with DEX 2.0, you can run an OpenID Connect provider on top of Kubernetes with no external databases. It actually uses the Kubernetes third-party APIs to persist the handful of pieces of data that an identity provider is required to have, which is really important. Before, people were having to run their own SQL database, and now it's all self-contained. You deploy Kubernetes, and the only data store that you have to worry about is an etcd data store. And then DEX is the default identity provider inside of Kubernetes, but it's all built on standards. There's tons of different vendors building OpenID Connect providers, and we're happy to plug in and use those things or use people's LDAP servers. All right, so I've covered a lot of stuff. It's quite a deep technical deep dive. I just want to reiterate what we've been doing over the last few years and some of the places that we're investing and will be continuing to invest into 2017. We're ensuring that this entire ecosystem is built on shared standards through the OCI and through our work integrating OCI specifications into Rocket and the rest of our products like Quay. We're going to be working with upstream to move Rocket support from about 90% complete to 100% complete. Again, people can try it out today, and we'll be doing that work in 2017. And we know that by having a container engine that's fully aligned with Kubernetes and its concepts around pods will help to drive faster innovation. We've worked end-to-end through etcd optimizations inside of the Kubernetes scheduler and work around caching and workload management inside of the Kubernetes API to ensure that Kubernetes is able to scale to 5,000 nodes and beyond. And then finally, we've been working on this architecture of self-hosted, which is what enables our idea in self-driving Kubernetes with Tectonic, to remove toil, to make it easier for people to maintain and operate these large distributed systems in a way that doesn't require a lot of manual intervention. And so we are, at CoreOS, experts at every level of the stack, and we're building open source projects and products that help to bring this whole thing to market. And I thank you for your attention, and I thank you for attending Tectonic Summit. Thanks.